Hello everyone, my name is Kunjila Kinghai. I am a PhD student from the Neuroscience Laboratory at the University of Strathclyde. My PhD focused on mental workload detection from EEG signals. I'm here to present my paper with the title EEG-based mental workload level estimation using deep learning models in collaboration with my supervisor, Dr. Yasha Morfati. Mental workload has been realized as a crucial component in human performance in a complex working environment. It found to be related to task performance, vigilance, situation awareness, and capability of handling emergency events. Too high or too low operator mental workload could have an effect on mental fatigue and human system performance. Conventionally, mental overload has been assessed through self-reported mechanisms such as SWOT or NASA-TLX questionnaire. However, to perform post-task self-reported feedback or performance measurement, subjects must be trained to understand the tools used for expressing their mental workload. So, such techniques could themselves increase subject workload. Thus, recent studies have investigated the possibility of predicting mental workload via neurophysiological signals like ECG, EOG, FNERS, or EEG. Among various neurophysiological markers, EEG is one of the most widely used signals for indicating a subject's brain electrical activity in response to cognitive stimuli and to predict the mental workload status effectively because of its portable measure and high temporal resolution. However, decoding mental workload level from EEG signal is not straightforward. Recently, machine learning techniques, especially deep learning, have been received much attention to capture variant characteristics in EEG signals and classify mental workload level accurately. In this study, we aim to classify the subject's mental workload level from EEG signal by using deep learning model named GRU, BGRU, BGRU-GRU, LSTM, BLSTM, BLSTM-LSTM, and CNN. The classification was performed by using a publicly available mental workload dataset named STILD. The EEG signals were collected using emotive epoch EEG headset via 14 electrodes, sampled at 128 Hz. Data is transmitted to a paired PC via wireless Bluetooth, and raw data is recorded with the emotive text-based software. These datasets contain EEG signals of 48 male subjects. They are from the university graduate population recruited via open email who don't have any neurological, psychiatric, or brain-related disease and never has taken part in any prior EEG experiment. In these experiments, the participants were asked to perform the SIMKAP multitasking activity. The signals have been recorded in resting state and working state. During the resting state, subjects sit on the chair for 3 minutes with their EEG being recorded. Then, in testing state, subjects complete a SIMKAP task and only the final 3 minutes of the recording were used for analysis. After each segment of experiment, subjects also estimate their workload status using a 1 to 9 scale questionnaires. The 9-point rating scale has been further categorized into 3 mental workload levels: 1 to 3 as a low, 4 to 6 as a moderate, and 7 to 9 as a high. Here, I will give you a brief introduction to the SIMKAP task. SIMKAP test module is a test created for measuring subjects' ability to concentrate and do several things simultaneously. During the task, the subject required to cause out identical items by comparing two separate panes while responding to the auditory questions, which can be arithmetic, comparison, and data lookup. Since the EEG signal can be easily contaminated by undesired noise or artifact, an automatic independent component analysis based on adjust was performed to reduce the noise in EEG signal before extrapolation. Then to capture only relevant EEG signal characteristic and also save the time and resource from unnecessary calculation features, we perform feature extraction. In this study, we took a sliding window with a range of 4 seconds and a tip of 1 second for feature extraction. This means each feature was calculated by using 422 sampling points with 384 sampling points overlapped. For the purpose of extensive using in previous study, we then choose the PSD alpha, PSD theta, skewness characteristic, approximate entropy, and Hertz feature as the optimal feature of the still dataset in this scenario. Additionally, we also perform feature standardization before further analysis by F-scale. In this study, we performed the classification in two tags. Tag 1 was resting state versus working state, and tag 2 was low versus moderate versus high mental workload level. And as the EEG signal have been measured over a period of time, so the signal can be considered as a time series data. Consequently, we train our deep learning model using a 5-fold time series cross validation. To do so, we use only the beginning part of the series of every subject to train the model and test the model using the data ahead of the training set to avoid the problem of information leaking and imitated a real-life implementation. Therefore, in this study, we split the data by the testing set conditions are ahead of the training set. As can be seen from the result, in task 1, BLSTM-LSTM provide the highest accuracy of 94.75%. However, in task 2, the BGRU-GRU is the best model, providing a classification accuracy of 83.03%. In this study, we also observed that the bidirectional model did not contribute much to the classification tasks. This might be because of the training strategy of the bidirectional model. To train such a model, we have to input data from both the past and the future into the model in forward and backward directions. However, in real-life scenario, we don't have a future value of time series for the present prediction time. Hence, as a future study, we aim to tackle the problem of how to perform a bidirectional model in time series data. Thank you for your attention.